welcome to this class of vibration engineering. In the previous classes we have studied about the free and force response of single degree of freedom systems and 2 degrees of freedom system. Today we are going to study about this vibration observers. So before going to study about this vibration observer, let us first review about the force response of a 2 degrees of freedom system. So in case of a 2 degrees of freedom system, a spring mass system is shown here. So M1 and M2 are the mass of this system, and K1, K2, K3 are the stiffness of the system. Let this mass M1 is subjected to a harmonic force of F sin omega t. So in this case already you know, to derive this equation motion, either you can go for this Newton's method by using the Newton's second law, you can derive the equation motion, or you may use the Lagrange principle or the extended Hamilton principle to derive this equation motion. So in this case already you have derived this equation, which can be written in this form: this mass matrix into x double dot plus stiffness matrix into x will be equal to this force vector, and as I am taking a harmonic forcing, then this can be written as F sin omega t. Here the first mass is subjected to a force F sin omega t, that is why you have a force in this form F 0 sin omega t. Here M11, M12, M21, M22 are the element of the mass matrix, K11, K12, K21 and K22 are the elements of the stiffness matrix. So already you know from the single degree of freedom system that when you are applying a sinusoidal force, then the response also will have similar frequency. So the frequency of the response will be in the form of sin omega t. So I can assume the response in this form x1 x2 equal to capital X1 capital X2 sin omega t for this system. So if I will substitute this solution in this equation, then it will reduce to, this form. So K11 minus M11 omega square, because this x1 double dot will becomes x1 into omega square sin omega t and with a negative sign. So it becomes minus M11 omega square x1. Similarly this M12 x2 double dot will becomes, so when I will substitute this equation, it will becomes minus M12 omega square. So I can substituting this equation in the previous equation, one can write it in this form: K11 minus M11 omega square, K12 minus M12 omega square, K21 minus M21 omega square and K22 minus M22 omega square, capital X1 capital X2. These are the modes, normal modes. So x1 and x2 sin omega t. So this is can be written in terms of f1 0 sin omega t. So the sin omega t and sin omega t you can cancel, and so this will reduce to this form, that is k minus m11 omega square, k12 minus m12 omega square, k21 minus m21 omega square and k22 minus m22 omega square into x1 x2 equal to f0. So this contains two algebraic equation with unknown x1 and x2. So you can solve these two algebraic equation to find x1 and x2. There are several methods to find this thing. Either you may go for this Cramer's rule to find if the equation motion will be of higher order, and as it is only 2 degrees of freedom system and you have only two unknowns, then you can simply solve these two equations to find the solution. So to find the solution, I can also use this inverse method. So if I am writing this as A matrix, then I can write this x1 x2 will becomes A inverse into, if this is F, so it will becomes A inverse F. So using these two, so I can write this x1 x2 equal to A inverse F. So this inverse equal to adjoint of A by determinant of A. So this adjoint matrix can be written in this form. So this is equal to K22 minus M22 omega square minus K12 M12 omega square minus K21 plus M21 omega square K11 minus M11 omega square and the determinant of matrix A, and then this is F0. So, this thing can be simplified to this form. So, one can write this x1 equal to K22 minus M22 omega square into F by Z omega. So, I have written this as Z omega, this is a function of omega. So, I am writing this lower matrix as Z omega matrix. So, this x1 will becomes then K22. So, you can see this thing by multiplying this. So, the x1 will becomes K22 minus M22 omega square into F, and this part is multiplied with 0. So, this becomes K22 minus M22 omega square F by determinant of this Z omega. So, that is written here K22 minus M22 omega square F by determinant of Z omega, and this x2 from this equation you can see x2 will becomes, so here you are multiplying minus K21 plus M21 omega square F, and this part is multiplied with 0. So, this into this by the determinant of Z omega is x2. So, this x2 equal to K21 minus M21 omega square by Z omega F. So, where Z omega I have already told you. So, this is the K11 minus M11 omega square, K12 minus M12 omega square, K21 minus M21 omega square, and K22 minus M22 omega square. So, from this you can find this x1 equal to K22. So, given the value of stiffness, so you can find K22, M22 and this omega and this x1, x2, the response you can find. So, let us take a simple example. Let us take the system, let us take this spring mass system. So, let us take 3 springs and 2 mass. So, it is supported by some roller, and this is K1, K2 and K3. This is M1 and M2. For simplicity, let us take this M1 equal to M2 equal to M. So, this becomes, this is I am taking as 2 kg, and then K1 equal to K2 equal to K3 let us take, and this is equal to K, and let us take this is equal to 100 Newton per meter, and it is subjected to, this fast mass is subjected to a force. So, this force F. So, this force equal to, let us take, it is equal to 5 sin 2t. Initially, let us take this force equal to 5 sin omega t, and then let us find for the special case when omega equal to 2 radian per second. So, already we have derived the equation motion for this case. So, the equation motion can also be derived by using this Lagrange principle. So, if you use the Lagrange principle, then the kinetic energy can be written as half m x dot square x1 dot square plus half m m2 x2 dot square, and the potential energy can be written like this. So, the spring K1 is subjected to a displacement of x1, this K2 is subjected to a relative displacement of x1 minus x2, and this spring K3 is subjected to a displacement of x2 only. So, this potential energy I can write U equal to half K1 x1 square plus half K2 x1 minus x2 square plus half K3 x3 square. So, here I am taking as no x3. So, this is x2 square, this K3 is subjected to a displacement of x2 only, and this is subjected to a displacement of x1. So, this is x2 square, and the kinetic energy is equal to half m1 x1 dot square plus half m2 x2 dot square, and the force vector qk generalized. So, I can take the generalized coordinate in this case if I am using this Lagrange principle as x1 and x2 are the generalized coordinates. I can take a physical coordinate from this base I can take a physical coordinate. Let the physical coordinate I am taking from this position, let this is r0. r0 is the distance from this fixed end to this equilibrium position. So, that is r0, and so the displacement of the first mass r1 I can write in this form. So, r1 I can write it is equal to, so r1 equal to r1 vector I can write equal to r0 plus x1I. So, the horizontal direction I can take x0. So, I can write this as r0 plus x1I. Similarly, I can take let the equilibrium position from this to this, let me put this distance equal to a. So, then this becomes displacement of 2. So, this r2 will become r0 plus a plus x2I. So, now to find the equation motion I can use this Lagrange principle, which tells d by dt of del L by del qk dot minus del L by del qk equal to qk. So, this capital Qk is the generalized force. So, this generalized force can be obtained by, so q1, to find q1 I can write this expression in this form. So, q1 will be equal to summation I equal to 1 to n. So, this becomes f dot del r I by del qk. So, in this case we have only one force, this force equal to f sin omega t is acting here, this force is f sin omega t. So, it is in the positive this direction. So, I am taking this direction as I with a unit vector I. So, this force equal to f sin omega t I, or I can write this force. So, only one force is acting. So, I can write this is equal to f, or simply I can write this as f1 equal to f sin omega t. So, I can write this is f1 I dot, so this del r I by del qk. So, q1 equal to x1 and q2 equal to x2. So, using this, so q1 when I differentiate with respect to q1 or x1, so this r1 gives only I. So, this becomes f1 I dot I. So, this becomes f1. So, the q1 generalized force q1 equal to f1, that is f sin omega t. Similarly, one can find q2. So, in this case you can find that there is no force, as no force is acting on mass 2. So, this q2 becomes, so this is fi. So, f1 into del r1 by del qk is x2. So, now k equal to 2. So, that q2 equal to x2. So, if you differentiate with respect to r1, this becomes 0. So, f1 dot 0 plus f2 dot, so as f2 equal to 0, so this becomes also 0. So, both the terms, that is f1, so this thing will be equal to f1 dot del r1 by del x1 plus f2 dot del r2 by del x2. So, as del r1 by x2 becomes 0 and f2 becomes 0. So, this is 0 and this is 0. So, the whole term q2 becomes 0. So, one can write the equation motion in the simple form. So, that is m1 0, or I have taken m1 equal to m2. So, I can write this is simply m. So, m0 0 m x1 double dot x2 double dot plus this is k1 plus k2 minus k2. So, this becomes, so k1 plus k2 becomes, so this becomes 2k. So, this is 2k minus k. So, this is 2k minus k, and this becomes minus k, and this becomes k, x1 x2 it becomes. So, I have 2 mass here, I have 2 stiffness. So, this becomes k2 plus k3. So, this becomes 2k. So, this equal to this thing equal to, I can write it equal to f sin omega t 0. So, now comparing this equation with the general equation I have derived before. So, this equation I can write this z omega. So, this z omega can be written in this form. So, z omega will give, so I can find this z omega, and z omega in this case determinant of z omega becomes m square into omega fourth minus 4 by minus, so this becomes, so I can write this equal to z omega equal to m square into omega fourth minus 4 k by m omega square plus 3 k square by m square. So, this thing can be simplified and can be written in this form, m square into omega square minus omega 1 square into omega square minus omega 2 square, and I can write x1 in this form. X1 will becomes 2k minus m omega square into f by z omega, determinant of z omega, that thing can be written as m square into omega square minus omega 1 square into omega square minus omega 2 square. So, here omega 1 square equal to k by m and omega 2 square equal to 3 k by m. So, substituting the value, you can find this omega 1 square equal to 50 and omega 2 square equal to 150. Similarly, x2 can be written in this form. So, x2 becomes kf by m square into omega square minus omega 1 square into omega square minus omega 2 square. Now, one can substitute the value of these omega 1 square, that is equal to 50, omega 2 square equal to 150. If one want to find the value at omega equal to 2, so we can obtain this x1 equal to 0.035 meter and x2 equal to 0.0186 meter. So, for omega equal to 2, so these are the value, and one can note from this expression that when this k by m, so this omega becomes, this omega square becomes this 2k by m, then this x1 equal to 0, or also one can see that when this omega square equal to omega 1 square or omega square equal to omega 2 square, x1 and x2 tends to infinity. So, x1 becomes 0 when 2k equal to m omega square or omega square equal to 2k by m, and x1 and x2 tends to infinity when omega square equal to omega 1 square or omega square equal to omega 2 square. Here omega 1 and omega 2 are the normal mode frequency of this system. So, these are the normal mode frequency, that thing can be written by k by m, omega 1 square equal to k by m and omega 2 square equal to 2k by m. So, in this way one can find the response of a forced vibration of a 2 degrees of freedom system. So, let us now study about the vibration observer of the system. So, in this problem, in this particular problem, we have seen that for some value of omega we are getting this x1 equal to 0. So, if we have a primary system or primary system with mass m1 and stiffness k1, we can, which is subjected to a force of f sin omega t harmonic force, then we can make its steady state amplitude x1 equal to 0 at some frequency. So, here we have seen that this frequency omega becomes minus, this omega becomes 2k by m. So, we can completely observe the vibration of a system by systematically designing this system or by systematically adding another spring and mass to the system, and by suitably arranging the frequency of the system, we can find or we can make this response of the primary system equal to 0. So, so this is the principle of vibration observer, which we are going to study in detail now. So, this is a primary system. So, we have many machineries which can be modeled as a single degree of freedom system. So, this is which can be modeled as a spring and mass system or spring and mass damper system. So, this is the primary system. Now, this primary system, let it is subjected to a harmonic force of F sin omega t. To observe this vibration, we have seen in the previous example, we have taken that as a 2 degrees of freedom system, where we have added or we have 2 spring and 2 mass. So, from this example, we have seen that we can observe that vibration by adding some spring and mass. So, here in this primary system, so I have added another spring and mass, and I will find the general expression for this vibration observer. So, let K1 is the spring constant of this primary system and M1 is the mass of this, and the additional observer has is spring constant or stiffness of K2 and mass of M2. This primary system is subjected to a force of F sin omega t. So, the equation motion of this system can be written using this Lagrange principle or Newton's method, and that thing can be written. So, that thing can be written in this form mx double dot plus kx equal to F sin omega t, which we will see in a few minutes after. So, in this case of primary system, already we know that the response of the system when it is subjected to a force F sin omega t can be written in this form. So, if there is some damping present, the steady state response of the system can be written in this form, x equal to F by k sin omega t minus phi by root over 1 minus r square whole square plus 2 zeta r. So, where phi is the phase difference between this response and the forcing frequency or forcing term, and this r equal to the frequency ratio, that is the external frequency and the natural frequency of the system, and this phi can be given tan phi equal to 2 zeta omega by omega n 1 minus omega by omega n whole square. But as we are studying a undamped system or system without damping, so in this case I can put this zeta equal to 0 and I can write this x in this form. So, x becomes F sin omega t minus phi by m into omega n square minus omega square, or I can write this expression in this form. So, I can divide this expression by k. So, I can divide k here and here. So, this becomes F by k and m by k equal to omega n square. So, I can write this F by k equal to 1 by 1 minus r square. This already we know this x by F by k is F by k is the static deflection, already we know. So, that is equal to x0. So, this x by x0 one can plot with respect to this omega by omega n, and one can see that at omega equal to omega n, that is omega by omega n, when it becomes 0, the response tends to infinity. The system will have a very large amplitude of vibration at omega equal to omega n. So, when the system when the excitation frequency equal to the natural frequency of the system, in the absence of damping, the system will resonate and it will the response tends to infinity. So, to observe this vibration, we should add this observer, and when we are adding that observer, so we can write the equation motion. To find that equation motion, we can use different method. So, let us use this Lagrange method to find that equation motion. So, in this case, the kinetic energy of the system can be written as half m1 x1 dot square plus half m2 x2 dot square, and the potential energy I can write it equal to U equal to half k into, so I will write k1. So, this k1, so in this figure, So, this has a displacement of x1 and this second mass has a displacement of x2. So, this spring K2 is subjected to a displacement which is relative displacement, that is x1 minus x2, and the spring K1 has a displacement of x1. So, the potential energy becomes half K1 into x1 square, and for potential energy of this becomes half K2 into x1 minus x2 whole square. You may note that this x1 minus x2 whole square equal to x2 minus x1 whole square. So, you need not have to bother about the sign whether this x1 is greater than x2 or x2 is greater than x1 when you are applying this Lagrange principle. So, in this case you can write the potential energy equal to half k x1 square plus half k2 x1 minus x2 whole square. So, you can write this k1 x1 square plus half k2 x2 square. Now, to derive the forcing function or generalized force. So, this is the system. So, in this system, like previous case also, I can take this physical coordinate r0. So, it has a displacement, let it has come to this position after displacement. So, this is x1. Similarly, this is the equilibrium position of this and it has come to this position, this is x2. And previously like previous case, I can write this as a. So, I can write this physical coordinate as r1. So, these two, this as r1. So, this physical coordinate I can write. So, r1 becomes r0 plus x1. So, I can take this coordinate. So, this direction as I and this direction as j. So, this becomes r1 plus r0 plus x1 I, and r2 becomes r2 vector become r0 plus a plus x2 I. So, I can find this qk, that is the generalized force in this case similar to the previous case, and you can find this q1 equal to f1 dot del r1 by del q1 plus f2 into del r2 by del q1. So, here q1 equal to, in this case similar to the previous case, here x q1 equal to x1 and q2 equal to x2. So, by applying the Lagrange principle, you can find the equation motion which can be written in this form. So, this equation motion reduced to m1 0 0 m2 x1 double dot x2 double dot plus k1 plus k2 minus k2 here k2 and x1 x2 equal to f sin omega t 0. And similar to the previous case, I can assume that this is the force vibration. So, the response frequency will be same as this forcing frequency. So, I can assume a solution, this x1 x2 equal to x1 x2 sin omega t. So, the frequency of the response equal to the frequency of the forcing function. So, you may note the forcing function has a frequency omega, and here the solution also we have assumed with a frequency omega. So, this x1 x2 can be written as x1 x2 sin omega t. So, by substituting this equation in this equation, I can write k1 plus k2 minus m1 omega square minus k2 and k2 minus m2 omega square into x1 x2 sin omega t will becomes f sin omega t 0, and I can delete this omega t terms. So, it will reduce to this form. So, the equation becomes k1 plus k2 minus m1 omega square minus k2 minus k2 minus m omega square x1 x2 sin omega t, this becomes f 0 sin omega t. So, the sin omega t terms can be deleted. So, this cancels. So, this equation becomes k1 plus k2 minus m1 omega square minus k2 minus m2 omega square x1 x2 equal to f 0. So, previously I used this inverse method to find x1 x2. Now, I may use this Cramer's rule to find this x1 x2. So, you know while finding using Cramer's rule, this x1, when you are finding x1, you can replace this column, this first column by f0, and when you are from this matrix, so you just replace, when finding x1 you replace the first column by f0, and when you are finding x2 replace the second column by f0. So, using Cramer's rule I can find x1 equal to f0 minus k2 minus m2 omega square by determinant of this matrix. So, while finding x1, you just recall that using Cramer's rule you have to replace this first column by f0 and take the determinant of that, then divide by the determinant of this z omega. So, this thing I am taking as z omega. So, you can write x1 equal to f0 minus k2, this is k2 minus m2 omega square by determinant of k1 plus k2 minus m1 omega square minus k2, this is minus k2 minus m2 omega square, or this thing becomes, so determinant of this becomes k2 minus m2 omega square into f minus 0. So, this becomes k2 minus m2 omega square f by determinant z omega, and x2 can be obtained from this also. So, when you are getting x2, so you just replace this second column by f0. So, this becomes k1 plus k2 minus m1 omega square minus k2 f0. So, this is the thing by the determinant of this. So, this becomes, so as it is multiplied by 0. So, this first term becomes 0 and second terms equal to minus k2f. So, this becomes minus minus, so plus k2f by z omega. So, determinant of z omega. So, you can see that this x1, so from this expression you can see that x1 becomes 0 when k2 minus m2 omega square equal to 0, k2 minus m2 omega square when becomes 0, x1 equal to 0. So, from this we can write, or we can find the principle of vibration observer. Before that, let us find the determinant of z omega. So, z omega, so this is the z omega matrix. So, determinant of z omega can be written in this form. So, this becomes k1 k2 minus omega m1 k2 omega square minus k1 m2 omega square minus k2 m2 omega square plus m1 m2 omega fourth. You may recall that this z omega matrix is same as the A matrix you have taken for the free vibration analysis of a 2 degrees of freedom system. So, this matrix or the determinant of this also can be written in terms of the normal modes or normal mode frequency of the system. So, if the normal mode frequency of the system are omega 1 and omega 2. So, this expression you can write in terms of omega square minus omega 1 square. So, this thing you can write. So, if you take this, so you can write this in the form of omega square minus omega 1 square into omega 2 minus omega 2 square multiplied by some constant. So, now I can write this z1. So, this z1, to find this normal mode I can solve this equation and find the frequencies. So, these frequencies can be obtained from this equation. I can substitute this omega square equal to lambda. So, these are the eigenvalues. So, by substituting this omega square equal to lambda, this reduces to a quadratic equation. So, in this quadratic equation or solving this quadratic equation, you can find the normal mode frequencies of the system. So, the normal mode frequencies of the systems are lambda 1 2 equal to 0.5, k1 by m1 plus k2 by m2 plus k2 by m1 plus minus root over k1 by m1 plus k2 by m2 plus k2 by m1 whole square minus 4 k1 k2 by m1 m2. So, from the previous equation here already I told you that x1 becomes 0 when you are taking omega square equal to k2 by m2. So, when omega square equal to k2 by m2, x1 becomes 0 and x2 becomes minus f by k2. So, this is the principle of vibration observer, that is when you are adding a additional mass and stiffness to the original system. Let this you have a original system, this is the primary system. So, let this is the primary system with m1 and k1. I am adding another system, secondary system with mass m2 and k2. So, if I will add this m2 and k2 in such way that, so this is subjected to a force F sin omega t. So, if I will add a mass and stiffness in such way that this omega square, that is the frequency of external excitation, becomes square of the frequency of external excitation becomes k2 by m2, then this vibration of the first mass will be completely observed, that is x1 equal to 0. And in that case you can see that this f2, when you are substituting omega square equal to k2 by m2, that time you may check that this becomes this expression z omega you can find, and you can see that this x2 becomes minus f by k2. So, the displacement of the second mass is limited by, this is limited by the stiffness of the second spring k2, and it shows that this force, whatever force we have applied to the first mass, is completely observed by k x2. So, f becomes k x2, and it shows that it is completely observed by the secondary system, that is k2 m2, what we have added to the primary system. So, already we have written this x1 equal to k2 minus m2 omega square f by the z omega can be written as k1 plus k2 minus m1 omega square into k2 minus m2 omega square minus k2 square, or if I will divide by k1 k2, I can divide it and I can simplify this expression in this form. And already I told you about the principle of vibration observer. So, to observe the vibration of a primary system, we have to add a secondary system in such way that the external frequency square will become k2 by m2, where k2 and m2 are the stiffness and mass of the secondary system. So, as you have seen before that we are interested at the resonant frequency, that is when the system, the natural frequency of the primary system becomes equal to the external frequency. So, that time resonance occur, and we want to suppress that vibration at resonant frequency. To suppress the vibration at resonant frequency, hence we should write the frequency equation in this form, that is omega 1. Already we know that omega 1 equal to root over k1 by m1 and should be equal to omega 2, that is root over k2 by m2. So, to observe the vibration near the resonant frequency, we can write this omega 1, that is natural frequency of the primary system, equal to the natural frequency of the secondary system, that is root over k2 by m2, equal to the frequency of the external excitation. And let me put this mu as the mass ratio, that is mass of the secondary system by the mass of the primary system, and as k2 root over k1 by m1 equal to root over k2 by m2, or k1 by m1 equal to k2 by m2. So, I can write this mass ratio equal to m2 by m1 equal to k2 by k1. So, by substituting this equation in the previous equation, that is k1 x1 by f, I can write this expression k1 x1 by f equal to 1 minus omega by omega 2 square by omega 4th by omega 1 square omega 2 square minus 1 plus mu into omega by omega 1 whole square plus omega by omega 2 whole square plus 1. You can find this from this. already I have written this thing k1 x1 by f equal to 1 minus omega by omega 2 square. So, this thing can be obtained by deriving the previous equation by k1 k2. So, if you divide this expression by k1 k2, so this k2 cancel, and if you rearrange these terms, so you can write this expression in this form. So, it can be written in this form k1 x1 by f equal to 1 minus omega by omega 2 whole square by 1 plus k2 by k1 already I told you this is can be written in terms of mu. So, this becomes 1 plus mu minus omega by omega 1 square into 1 minus omega by omega 2 square minus this k2 by k1 is written in terms of mu. So, you can write this expression in this form, and k2 x2 by f also can be written by 1 by omega 4th by omega 1 square omega 2 square minus 1 plus mu omega by omega 1 square plus omega by omega 2 square plus 1. So, this frequency ratio this magnification factor, that is k1 x1 by f, is written in terms of the natural frequency of the primary system, that is omega 1, and the natural frequency of the secondary system, that is omega 2, and the mass ratio mu. So, by using this I can write x1 by xxt is nothing but f by x1, that is the static deflection of this primary spring or the primary system. So, x1 by xxt equal to 1 minus omega by omega square whole square by omega 4th minus omega 2 square minus 2 plus mu into, so 2 plus mu into omega by omega 2 whole square plus 1. Similarly, x2 by xxt, in xxt also it is equal to f by k. So, this becomes x2 by f by k. So, this xst is nothing but f by k1, that is the initial or the static deflection of the spring k1. So, from this expression this x2 by xxt can be written by 1 by the lower expression. So, this becomes x2 by xxt equal to 1 by omega 4th by omega 2 square minus 2 plus mu into omega by omega 2 whole square plus 1, and using this expression one can plot. So, it is plotted. So, we have taken one example where m1 equal to 10 kg, k1 equal to 1000 Newton per meter, m2 equal to 1 kg and k2 equal to 100 Newton per meter. So, in this case it is assumed that, so m2 by k2, you just see m2 by k2 becomes 100, and this k1 by m1 by k1 also it becomes 100. So, in both the cases I have taken this omega 1 equal to omega 2, and when this, so here I have plotted this with respect to omega by omega 2, so which is omega 2 also equal to omega 1. So, when, so you can see that previously you have seen that when omega becomes omega 1, that is omega by omega 1 equal to 1, you had seen the system had a huge response. The system had this, the response of the system became infinity in that case. So, this dotted line show the response of the system, primary system, when omega equal to omega 1, but in this case you have seen that this becomes 0, this becomes completely equal to 0, this response becomes completely equal to 0 at omega equal to 1. So, in this way we have observed the vibration at the resonant frequency of the system, but while observing this vibration you can observe that this resonant frequency this resonant frequency is shifted to, one is shifted to left side and right side. So, now the resonant frequency becomes 0.8, around 0.8 and 1.2. So, instead of having one resonant frequency at omega equal to 1, so now we have two resonant frequency that is one at 0.8 around 0.8 and other at 1.2. As we are observing this vibration at this particular frequency omega equal to omega 1, this type of observer are known as tuned vibration observer. So, in case of tuned vibration observer, it observe the vibration at a particular frequency. Also, it depends on the mass ratio of the system. I have already written this expression of this x1 k1 by f in terms of the mass ratio. Also, you have observed that this x2 expression for x2, that is x2 becomes, so x2 becomes f by k2, x2 equal to f by k2. So, at resonant frequency, that is when omega equal to omega 1 equal to omega 2, though x1 becomes 0, x2 becomes, so x2 becomes f by k2. So, in this case, if we are taking a stiffness of 100 Newton meter, if we are applying a force, let we are applying a force of 5 Newton, then we will have this x2 will becomes 5 by 100. So, 5 by 100 meter. So, it will have a huge response. The second mass or the secondary mass will undergo a large deflection. So, to avoid that large deflection, we have to increase the value of k2. So, if we are increasing the value of k2 without changing this value of m2, so that time it will not be a observer. So, we have to increase this value of m2 also to keep omega 2 constant. So, to reduce k2, so to reduce k2 we have to, so to reduce x2, we have to increase k2. So, we have to increase k2. So, when we are increasing k2 simultaneously we have to increase m2. So, if we are increasing this m2 also, then we may need a large secondary mass to observe the vibration. So, this is the limitation of this tuned vibration observer. So, if we plot this response, already we have plotted this, and if we see this thing again, if you write this is equal to, so this becomes x1 k1 by f, that x1 k1 by f. So, this expression x1 k1 by f, this is omega by omega 2. So, here you have not clearly seen this response. So, in a clear form it is plotted here. So, you can see this response. So, at omega equal to omega 2 equal to 1, you can observe that this response becomes 0, and here the response, but the resonant frequency is shifted to this. So, in this case the absolute value of the response is plotted, that is x1 by k1 f. So, if you are not plotting the absolute value, then the response curve will look like this. So, this will be the response curve for a particular value of mu. So, this is plotted for mu equal to 0.25. So, already I told you to have less value of x2, so which is equal to f2 by k2. So, you have to increase this stiffness. So, to increase this stiffness, you have to increase this mass ratio, mass m2. So, to increase mass, to increase the secondary mass, one should have, the secondary system will have a very huge mass, and that will be the limitation of the vibration observer. So, one should have to compromise this value of this mass m2. So, the one should take the mass ratio in such way that, or one can compromise this thing usually and keep this mass ratio usually kept between 0.05 and 0.25. So, by keeping this mass ratio between 0.05 and 0.25, x2 can be limited to a certain extent and x1 can be made to 0. So, if one plot this mass ratio, this omega by omega 2 versus mass ratio, one can obtain this curve for this omega 2 by omega 1 equal to 1. So, for tuned observer you can observe that you have two frequencies, that is this frequencies omega at 2 points. So, the resonance will occur at these two frequencies corresponding to this frequency and this frequency for a particular value of mu. So, by using a tuned vibration observer you can observe the vibration of the system at a particular frequency, but in many machines like these IC engines the resonance occur or resonant frequency is a function of the function of the frequency of the excitation of the system. So, in case of a IC engine, so let me draw for a IC engine. So, you have a crank and this is the piston cylinder arrangement. So, in this piston cylinder arrangement, so due to the unbalanced force of this reciprocating mass, due to this unbalanced force of the reciprocating mass, the system has a unbalanced frequency, unbalanced force with multiple frequency which are proportional to this rotation of this crank. So, if the crank is rotating with frequency omega and you are changing this frequency of the crank, then one can find the unbalanced force at a wide range of frequency. So, in this case, to avoid this frequency or avoid this resonant conditions or to avoid this unbalanced force, so one will not be able to use this tuned vibration observer, as the tuned vibration observer is applicable for a particular frequency. So, it cannot be applicable for a system in which the unbalanced forcing frequency is a function of this rotating frequency. So, in that case one should go for a pendulum, centrifugal pendulum observer. So, in case of a centrifugal pendulum observer, so this is the disc or this is the crank rotating with frequency omega. So, let it is rotating with frequency omega and we have to add a pendulum at any point. So, on this disc let us add this pendulum. So, this is a simple pendulum with mass m and it has a length r. So, in this case I can write, so let me take, so let theta is the rotation at time t, theta is the rotation of the crank or the disc and phi is the rotation of this pendulum. So, original in case of phi very large, the system will be a nonlinear system, but we will limit our analysis to a linear system by assuming that this phi is very small. So, in this case I can write this pendulum has a mass m and it is rotating with phi. So, I can find the force of this pendulum. So, the force of the pendulum can be obtained by finding the acceleration of the pendulum. So, the acceleration of the pendulum can be written in this form. So, the acceleration of this pendulum equal to the acceleration of point, let this is origin O and this point is O dash. So, O dash is the point at which this pendulum is attached. So, the acceleration of point m or mass m can be written as the acceleration of point O dash plus acceleration of m with respect to O dash. So, this acceleration can be divided into two parts. So, let me put a coordinate system, this is I along this direction and perpendicular to this j, and so I can write this acceleration of this mass m with respect to this origin O dash and it can be written in this form. So, let this r is the, let r is the radius of the crank. So, if r is the radius of the crank and small r is the length of the pendulum, so point O dash will have the acceleration. So, velocity, first the velocity of this point equal to angular velocity equal to theta dot, and angular velocity of this pendulum becomes theta dot plus phi dot. So, the acceleration of this point, if it is rotating with uniform velocity, then this angular acceleration becomes 0, but if it is not rotating with uniform velocity, we can write this angular acceleration equal to theta double dot. So, I will have two component of this acceleration here. So, this becomes r theta double dot and another component equal to r theta dot square in this direction. Similarly, for this pendulum, I will have the acceleration, two components of the acceleration, one is the centripetal component and other will be the other component will be the radial component. And by using this acceleration, I can write this acceleration a m equal to r theta double dot sin phi minus r into theta dot plus phi dot square minus r theta dot square cos phi I plus r theta dot square theta double dot cos phi plus r theta dot square sin phi plus r into theta double dot plus phi double dot j. So, this is the acceleration term. So, using this acceleration I can find this force, and as the pendulum is attached to this point, the moment of this pendulum about this point equal to 0. So, I will have only the j component, and from the j component I can find the natural frequency of the system. So, by deriving in that way I can find the natural frequency of the system will becomes, or in the next class I am going to show you that the natural frequency of the system becomes this equal to r by r into n square, where n is the rotational speed of this crank. So, in this way you can find, I have told you about two different types of observer, one is the tuned vibration observer and other one is the centrifugal pendulum observer. In the next class I will tell about the centrifugal pendulum observer in detail, and I will tell how this observe the vibration at different frequency or at a wide range of frequency.